This video will be about some example problems of constructive and destructive interference. This first example is two loudspeakers, all right, separated by 3.5 meters. This is a square each side with that length. And what you do is you move from A to a corner, all right, and you go from constructive to destructive interference, and you only hear that change once, all right? So since you only hear that change once, here, since both points are equidistant, all right, we know delta L is equal to 0, okay, which tells us from our previous notes here, okay, about destructive and constructive interference, right, what we're looking at is for some integer multiple of the wavelength. When that integer multiple is 0, okay, and we're going from constructive to destructive interference, and we're going to the first location of destructive interference, n is still equal to 0. And that path difference, therefore, at the corner, all right, from both speakers, is going to be half lambda. Okay, that would be the first place you hear destructive interference. So it's just going to be 0 plus 1/2 lambda, again, going back to these notes right here, and we were looking at the equation for destructive interference right there. Okay, so we come over here and we see with some geometry, okay, that this side of the triangle, okay, is 4.95 meters. This side here is 3.5. The difference between those two is 1.45 meters. Therefore, the wavelength, according to this formula when we solve for, is twice that path difference, 2.9 meters. All right, so that is that first example. So the second example here, okay, what it tells us is that we have the same setup as above, all right, but now we have a tone that we know F is equal to 700 hertz. Okay, so what happens along the way, all right, is that we go from constructive to destructive, then constructive to destructive, and constructive to destructive again. So I'm going to label this here constructive, we end up at destructive, and in between we switch back and forth 3 times. So something like this here, destructive here, constructive here, destructive here, and constructive here. Okay. So by the time we get down here, this is n equals 0. All right. This is n equals 1. So this is n equals 2. All right. So what we know from this, all right, is that n equals 2. Therefore, delta L has to be equal to 2.5 lambda. All right. And we're going to end up solving for lambda. So if we look at our delta L from the previous one, all right, I believe right here where we had 1.45 meters, so 1.45 meters equals 2.5 lambda. All right, when we solve for lambda here, just divide by 2.5, and you end up with 0.58 meters as the wavelength of the sound. Okay, so now we just want to figure out what is the speed of sound in air. Well, as long as we have lambda and f, we can figure that out. 0.58 meters times 700 hertz, and when you plug that in, you should end up with 406 meters per second. And no, I'm not paying attention to sig figs here. Forgive me. Okay, so 400 meters per second with sig figs there. All right. So this next question then, okay, it wants us to answer this. All right. Now we'll be looking at this in one dimension here. But we have two speakers. They both emit a frequency of 300 hertz. And what they want to know, all right, is they're placed in a line. Location A is the first place along the line joining them where you can stand and hear no sound. How far apart are the speakers? Okay, so what we have here, all right, A being the first place that we don't hear any sound. Again, this is n equals 0. All right, and we got delta L, okay, is equal to 1/2 lambda. All right, so what we're looking for is what delta L is equal to. All right. And therefore, to get lambda, what we want is delta L, which is their separation. That's the path difference right here. So in order to do that, we need lambda. And we can use this wave speed from the previous problem in order to do this, all right? And we know the frequencies. So from this, we can get lambda All right, it's just going to be B divided by F. And I'll just substitute this in my calculator really quickly. 6. Okay, what we end up with here on lambda is 0.74 meters. Okay, and when we solve for delta L, 1/2 of this, all right, and that should be 0.37. Okay, so that's how far apart both of these speakers are. Okay, so that's it. All right, and yeah. Oh, wait a minute. You know what? I think I reversed that. Sorry. Quick little mistake here. Quick little math error. I'm sorry about this. Let me just switch this around. Okay. Really, really quickly. 406 divided by 300. There we go. 1.35. Go with. Okay. With rounding there. All right. There we go. That's what it should be. I'm sorry. Quick little math error. So I actually divided there in the wrong way. So in class we'll go over this, but these are just some good quick examples of interference.